before safety regulations, before labor unions had power, and before anyone thought twice about the men who built America's railroads, there were tools. Simple, brutal implements that could crush a hand, ignite an explosion, or end a life in seconds. These were not defective products. They were standard equipment, used daily by workers who knew the risks and took them anyway. Today, we're counting down 15 of the most dangerous old railroad tools that no longer exist. Number 15. The link and pin coupler. Before automatic couplers existed, connecting railroad cars required a brakeman to stand between two moving freight cars with a heavy iron link in one hand. As the cars came together, he had to guide that link into a receiving pocket on one car while simultaneously lining up with the other. Then he dropped a pin through the assembly to lock it in place. One moment of hesitation, one slip, one miscalculation of timing, and the cars would crush his hand, his arm, or his entire body. In 1888 alone, coupling accidents killed 300 railroad workers and injured over 6,700 more. Nearly 40% of all rail yard injuries involved these couplers. Mangled hands and missing fingers became the unofficial badge of an experienced brakeman. Railroad superintendents reportedly checked prospective employees' hands during interviews. Too many fingers meant inexperience. Too few meant you'd survived long enough to know the job. The link weighed about 7 pounds of solid iron. The pin weighed another 2 pounds. Congress finally outlawed link and pin couplers with the Safety Appliance Act of 1893, giving railroads 7 years to replace them. By 1902, coupling accidents had dropped dramatically. Sometimes progress is measured in fingers saved. Number 14. The tamping iron. Railroad construction in the 1840s required blasting through rock to level ground for track beds. Workers drilled holes into solid rock, packed them with gunpowder, inserted a fuse, covered it with sand, and then used a tamping iron to compact everything tight. The tamping iron was a pointed steel bar, typically 3 to 4 feet long and weighing 12 to 15 pounds. Every blow against rock risked striking a spark. Every spark risked igniting the powder prematurely. Phineas Gage became the most famous tamping iron victim in history in 1848. Working on the Rutland and Burlington Railroad in Vermont, he accidentally struck his iron against rock before the sand had been added. The powder exploded, driving the 13-pound iron completely through his skull, entering below his left cheekbone and exiting through the top of his head. Miraculously, Gage survived, though his personality was permanently altered. His case became a landmark in neuroscience, teaching doctors about the brain's frontal lobe. But Gage was one of the lucky ones. Countless other workers died instantly from similar accidents, their names never recorded. The tamping iron fell out of use as dynamite, and safer blasting techniques emerged in the later 19th century. Number 13. The rooftop brake wheel. Before George Westinghouse invented air brakes in 1869, stopping a freight train required human beings to physically apply brakes to each car individually. The brake wheels sat on top of freight cars, exposed to every element. When the engineer whistled the signal, brakemen would climb onto the moving train and run across the rooftops, spinning each wheel to engage the brakes below. In rain, they slipped. In snow and ice, they fell. In summer heat, the metal roofs burned their hands. Low bridges and tunnel overhangs struck them without warning. One stumble, one patch of ice, one miscalculation of distance, and they tumbled between the cars to be crushed under the wheels they were trying to stop. The brake club, a heavy wooden baton used for extra leverage on frozen wheels, became both tool and liability. A stuck wheel that suddenly freed could throw a brakeman off balance and into the gap between cars. In 1889, 1 in 12 workers in the running trades was injured on the job annually. Westinghouse air brakes made rooftop work unnecessary by allowing engineers to control brakes from the locomotive. But railroads resisted adoption for decades because of cost. The Safety Appliance Act of 1893 finally mandated air brakes, retiring the rooftop brake wheel to history. Number 12. The railroad torpedo. When visibility dropped to zero in fog, snow, or darkness, and when communication failed, railroads needed a way to warn oncoming trains of danger ahead. Their solution was a small explosive device strapped directly to the rail. The railroad torpedo, invented in 1841, contained black powder in a coin-sized metal housing with lead straps that wrapped around the rail. When a locomotive wheel crushed it, the resulting explosion was loud enough to alert even the sleepiest engineer. In theory, torpedoes were brilliantly simple. In practice, they were unstable explosives carried in workers' pockets, stored in cabooses, and handled by men with no explosives training. Old torpedoes became increasingly volatile over time. Temperature changes, moisture, and rough handling all increased the risk of premature detonation. Flagmen carried these devices for miles in darkness, stumbling over ballast and ties while essentially armed with dynamite. The formula was potassium chlorate, sulfur, and sand, designed to detonate under pressure. But aging torpedoes sometimes went off from impact during transport. Modern radios and electronic signals have almost entirely replaced torpedoes. A few railroads still carry them for emergencies, but they remain relics of an era when warning of danger meant risking your life. Driving railroad spikes required swinging a 10 to 12-pound sledgehammer hundreds of times per day. The spike maul had an elongated head, over 12 inches long, specifically designed to reach spikes on the far side of the rail without breaking the handle. This unusual shape required exceptional accuracy. A missed strike could glance off the spike and hit the worker's leg, ankle, or the arm of the man holding the spike. The striking faces of spike mauls would mushroom over time from repeated impact, forming dangerous metal lips that could break off as high-velocity shrapnel. Cracked handles were supposed to be replaced, but railroads were notoriously stingy with equipment. Workers used damaged tools because replacements never came. The physical toll was enormous. Gandy dancers, as track workers were called, swung spike mauls in the blazing sun and freezing cold until their bodies gave out. Hearing damage from the constant ringing of metal on metal was universal. Back injuries were routine. Crushed fingers from missed swings were so common they barely merited mention. Modern spike driving machines have replaced most manual spiking, but for over a century, the spike maul represented the brutal reality of railroad construction. 3 blows to drive a spike, millions of spikes per mile. Number 10. The Fusee. The railroad fusee looks like an ordinary flare, and that is exactly what it is. It is a pyrotechnic device that burns bright red for 10 to 20 minutes, providing a visible warning to approaching trains. The problem is, what happens while it is burning? Fusees ignite at 191 degrees Celsius, but they burn at 1,600 degrees, hot enough to cause severe burns on contact. The burning slag drips constantly, and inexperienced workers who wave them like lanterns pepper themselves with molten metal. One engineer recalled watching a new conductor come back to the cab with dozens of smoldering holes in his arms and coat, having learned the hard way that fusees are held stationary, not waved. In winter, workers carried fusees inside their coats to keep them functional, essentially strapping incendiary devices to their bodies. On hot summer days, improperly stored fusees could spontaneously ignite. Near flammable cargo, a single fusee could turn a minor delay into a catastrophic fire. The steel spike on railroad fusees, used to anchor them upright in wooden ties, added another hazard. Workers impaled themselves on those spikes in darkness. Fusees remain in use today, but their role has diminished dramatically with modern communications. The burns they caused are well remembered by generations of railroad workers. The clawbar was the essential tool for removing railroad spikes. It was a heavy steel bar with a curved claw on one end, designed to grip spike heads and lever them out of the tie. Simple in concept, brutal in execution. Removing a single spike required tremendous force, especially on spikes that had been driven years earlier and rusted into place. Workers had to position themselves carefully, find solid footing on uneven ballast, and throw their entire body weight into each pull. One slip meant falling backward onto the rock bed. One stuck spike that suddenly released could send the bar flying back into the worker's face. The claw bar's weight, typically 15 to 20 pounds, made it exhausting to use over an 8-hour shift. Experienced workers developed permanent calluses and often suffered chronic back problems. The pinch tip on the opposite end, used for prying tie plates, added another injury risk. Workers prying frozen plates would sometimes have the bar slip and drive the pinch tip into their hands, legs, or feet. The force required to free a corroded spike was exactly the force that could drive that tip through flesh. Modern spike pullers have replaced most manual clawbar work, yet the tool defined railroad maintenance for a century. Aligning railroad track was a team effort, requiring perfect coordination, and the lining bar was the tool that made it possible. These steel bars were 5 feet long and weighed over 20 pounds. Workers used them to shift entire sections of rail and ties back into proper position. They would jam the bars into the ballast, create a fulcrum, and then heave in unison, inching the track fraction by fraction. The work was performed under the direction of a caller whose chants kept the gang synchronized. One worker pulling out of rhythm could injure everyone. The force generated by 12 men pulling together was enormous, and if someone lost their grip or footing, that energy had to go somewhere. Flying lining bars struck workers in the face, chest, and head. The synchronized heaving motion, performed thousands of times per day, destroyed backs, shoulders, and knees. Heat exhaustion was constant in summer months. In winter, frozen hands could barely grip the cold steel. The work was so physically demanding that men who weighed less than 160 pounds often could not generate enough force to be useful, while those over 185 pounds risked being thrown off balance. Mechanized track alignment has replaced lining bars on major railroads, but for generations, bending iron to human will require human bodies to pay the price. Number 7. The track torpedo signal gun. While standard torpedoes were placed on rails by hand, the torpedo signal gun allowed workers to deploy explosives from a distance. This brass device, shaped like a small cannon, was mounted to the rear platform of cabooses and could launch torpedoes onto the track behind a stopped train. In theory, that meant workers would not have to walk back along the track in dangerous conditions. In practice, it meant aiming an explosive projectile at a narrow steel target while standing on a moving or recently stopped train. Misfires were common. The launching mechanism required careful maintenance, which rarely happened. Torpedoes would jam in the barrel, fail to ignite, or launch at unpredictable angles. Workers reported torpedoes bouncing off rails and detonating in the ballast, or worse, rolling back toward the caboose. The powder charge that propelled the torpedo added another layer of risk. Damp powder caused weak launches. Old powder could ignite prematurely. The brass barrel corroded in humid conditions, causing friction that could trigger the device unexpectedly. By the mid-20th century, railroad communication had advanced enough that torpedo guns became obsolete. But for decades, rear-end protection meant trusting a temperamental cannon loaded with explosives. Number 6. Rail tongs. Moving sections of steel rail by hand required specialized tools, and rail tongs were the most dangerous of them all. These enormous scissor-like implements clamped onto a rail's head, allowing workers to lift and carry sections that weighed up to 140 pounds per yard. A standard 39-foot rail tipped the scales at over 1,800 pounds. Moving it required multiple workers with multiple sets of tongs, all lifting and walking in perfect coordination. One stumble, one dropped tong, one worker out of sync, and the rail would come crashing down. Men lost feet, legs, and lives when rails fell. The tongs themselves could crush fingers if grip pressure shifted during a lift. Workers had to maintain constant tension while walking over uneven ground, navigating ties and ballast. The handles offered minimal grip, and sweat made them slippery. In summer heat, the rails themselves became too hot to touch, burning through work gloves. In winter, frozen steel stuck to skin. The sheer physical demand of lifting rails destroyed men's bodies within years. Hernias, crushed vertebrae, and torn muscles were occupational certainties. Modern rail cranes and mechanical loaders have eliminated most manual rail handling. But the tongs remain a symbol of how railroads once viewed workers as more expendable than equipment. When railroads needed to blast through mountains or remove rockfalls, they turned to dynamite. It required a detonation device. The dynamite plunger, also called a blasting machine, was a T-handled box that generated electrical current when pressed. Workers would connect copper wires from the plunger to blasting caps embedded in dynamite, retreat to what they hoped was a safe distance, and push the handle. Simple in theory, terrifying in practice. Faulty wiring could create short circuits that detonated charges prematurely. Damaged plungers generated weak current that failed to detonate all charges, leaving workers to investigate unexploded dynamite. Static electricity from the copper wires could trigger caps during setup. The countdown before detonation was often just a shouted warning. Misfires were especially dangerous. Workers approaching unexploded charges had no way of knowing if the dynamite was simply delayed or genuinely failed. Many died when they got too close and the charge finally fired. Modern blasting uses electronic delays and remote detonation systems with multiple safety interlocks. The hand-cranked plunger has become a museum piece, but it built the transcontinental railroad, one explosion at a time. Number 4. The Crosstie tongs. Replacing wooden crossties meant handling 200-pound chunks of creosote-soaked timber, and Crosstie tongs were the tools that made it possible. These heavy iron implements resembled oversized ice tongs with curved jaws that bit into the tie's wood when lifted. Two workers, one at each end, would grip, lift, and carry the tie to position before dropping it precisely between the rails. The creosote preservative that protected ties from rot also made them incredibly slippery. Tongs would lose grip without warning. A dropped tie could crush a foot or break a leg. The momentum of swinging a 200-pound object while walking backward was nearly impossible to control. Worse, creosote was toxic. Workers handling ties developed severe skin rashes, respiratory problems, and higher rates of certain cancers. The chemical burned eyes and made cuts refused to heal. Men who worked tie gangs for years absorbed enough creosote to affect their health permanently. The ties themselves had hazards beyond their weight. Old ties harbored spikes, spike holes, and splinters that could drive through boots. Damaged ties would sometimes split during lifting, sending workers sprawling. Modern tie machines insert and remove ties mechanically, but the tongs that handled millions of cross ties left their mark on generations of track workers. Number 3. The steam locomotive oiler can. Steam locomotives required constant lubrication, and someone had to apply it. The oiler can was a simple brass or copper vessel filled with thick, lubricating oil, fitted with a long spout for reaching moving parts. The catch was that oiling often had to happen while the locomotive was running. Oilers climbed onto moving engines and reached between spinning drive rods to apply lubricant to rod bearings, crosshead guides, and valve gear. One slip meant being pulled into the machinery. The connecting rods on a moving locomotive swung in complex patterns that could catch a sleeve, a finger, or an entire arm before the victim even realized their mistake. The main rod alone moved with enough force to crush bone like kindling. Heat was another constant danger. Oil ports sat near steam pipes and fireboxes. Burns were routine. Spilled oil on hot metal created smoke and sometimes fire. The oil itself was hot, kept warm in reservoirs to maintain proper viscosity. Workers poured it from height, trying to hit small cups on moving parts. A miss meant burns or wasted lubricant. Modern diesel and electric locomotives use sealed lubrication systems that require no intervention while running. But steam power demanded human beings put themselves inside the machine. Number 2. The blacksmith's rail nipper. Before factory-cut rail sections, railroads relied on field workers to cut rails to length on site. The rail nipper was essentially an enormous set of hardened steel jaws mounted on a lever system. Workers would clamp the nipper onto a rail, then hammer the lever or have multiple men pull it to shear through solid steel. The force required was tremendous, and the potential for catastrophic failure was always present. When nippers cut, they sometimes sent metal fragments flying at lethal velocity. The sheared edge of cut rail was razor sharp and left jagged burrs that sliced through gloves and flesh. Workers steadying the rail during cutting positioned themselves directly in the danger zone. If the nipper slipped during the cut, the stored energy released explosively. Flying handles broke jaws and fractured skulls. The cutting edges of nippers required constant maintenance. Dull edges required more force, increasing the risk of slippage. Chipped edges created unpredictable cuts and dangerous metal fragments. Workers often used damaged tools because replacements meant delays that foremen would not tolerate. Modern rail saws and torches have replaced mechanical cutting. But the nipper exemplified how railroad work transformed men into machines. Number 1. The Johnson bar. At the top of our list sits the simplest and most dangerous tool of all. The Johnson bar was the main throttle control on steam locomotives, a massive lever that controlled the valve gear and that determined how much steam entered the cylinders. Moving it required brute strength, and moving it incorrectly could kill everyone aboard. The Johnson bar controlled the cutoff, the point in each piston stroke where steam admission stopped. Engineers had to adjust it constantly based on speed, grade, and load. A wrong setting could cause wheel slip at speed, derailing the train. Too much steam could overspeed the locomotive and cause a boiler explosion. The lever was heavy, often requiring both hands and significant force to move. Engineers working 12-hour shifts grew exhausted, and tired hands made mistakes. The bar's position affected reversing, and accidental reversal at speed would tear the locomotive apart. Stories abound of engineers crushed when locomotives derailed and the Johnson bar impaled them. Others burned to death when boiler explosions followed loss of control. The bar had no safety interlocks, no backup systems, no forgiveness. It was simply a lever that held lives in its position. Modern locomotives use electronic controls with redundancies. The Johnson bar belonged to an era when one mistake meant catastrophe. And that's all, folks. These tools remind us that the railroads were built with blood, sweat, and sacrifice most of us can barely imagine. If you enjoyed this journey through railroad history's dark side, hit subscribe for more stories of the machines that made America. Here is another video I have specially selected for you. See you next time.